let's give this a go. Okay, so we had recently just finished up on the exponentials and logarithms side of things, finishing up with the applications of such. Next up for most people is the circular functions stuff. So that's what we'll be looking at for the majority of the rest of these classes. So if you are doing Unit 1 and 2 and you're not up to this, doing something else, let me know. Happy to change the curriculum to match what people are actually going through. I've got one planner that I'm referencing for another student just doing Unit 1 and 2, so I'm hoping this is in line with what you guys are doing. If not, again, let me know. Especially if they're tougher topics, because then we really want to make sure we're clarifying what's going on there. But okay, so circular functions, what's going on here? This is where you start using sine, cos, and tan in other applications than just finding the trig ratios, just doing like your SOHCAHTOA stuff. You start being able to plot those on graphs, and you start knowing how to evaluate the angles and turn them into specific values. And the way we do that is with reference to this thing called the unit circle. So the unit circle, by definition, is a circle that has a radius of 1 and it is centered at the origin. So you can see we've got our xy axis going on there, and there is a circle. So radius 1 means it's intersecting at plus minus 1 for each of the x and y intercepts respectively, and it's centered at the origin. Now, why do we use a unit circle for this? Well, it's got to do with the fact that we're allowed to now, or we're able to now, use angles with reference to where they would exist as of the origin. And it also allows us to convert, okay, what happens if we had a line that was tangent off of that angle, such that it intersected the circle at a certain point? What would the coordinates on that circle be? That's effectively what's happening here. Some basics here. So typically we're going to start moving into using radians more often than you otherwise might be used to. I know up until like pre-method you're usually using degrees for the trig ratio stuff. What we will typically be using will be radians instead. There is a conversion to get from one to the other. It's essentially, if you want to turn it into radians, you'll multiply your value by pi, divide by 180, or if you want to go to degrees, the other way around. So there's conversion formulas there for you to use, but to give you a more conceptual understanding of what's going on, what the hell is radians, well, if you think of the circumference of a circle as given by 2 pi r, then when you have a radius of 1, the circumference of that circle is 2 pi. What radians is effectively is a measurement of angle, but with respect to how much of the circumference is being taken up, you can think of it as, which is why an angle of 2 pi means the entire circle, right? It's 360 degrees. You've gone from start to finish all the way around. Whereas pi would be half of that. Pi on 2, half of that again. So it's a measurement with respect to the circumference of the circle, which is why we're able to make an equivalence of 2 pi and 360 degrees, and effectively with these conversion formulas all we're really doing is rearranging to get one on the other side, right? Like dividing by 2, multiplying by pi, or other way around. So if we look at an example, converting 3 pi on 4 to degrees. A nice little tip to think about. Yes, you have these equation formulas, but sometimes it's a bit confusing when to use what. The way I think about it is, if it has pi in the value, you want to get rid of the pi. So if you're going to put pi in the top or in the bottom of the fraction, the only way to actually remove it from the number that you have is to have it as a divisor. Right? 3 pi on 4, multiply by 180, divide by pi, because now you can see the pi on top and the pi on bottom will cancel out, leaving you with just a number, which is going to be the number with degrees. Same idea here, right? 270, there's no pi currently in it, it's in terms of degrees, so you want to make sure that what you have as your final answer has pi in it. So you're going to multiply by pi and divide by 180. that's pretty much it so far. Any questions about any of that? Cool. Next up, just a refresher on the trig ratios. This was that SOHCAHTOA stuff that I was talking about before. SOHCAHTOA is the acronym that is a way which you can memorize how the trig ratios are calculated with respect to the side lengths of a triangle. So sine being the opposite over hypotenuse, that's the SO. Cos being adjacent over hypotenuse, CA. And then TOA for opposite over adjacent. As a refresher, the hypotenuse is always the longest length of your right angle triangle. The opposite and the adjacent are determined purely based off of where the angle is located. So if the angle is located here, as in the picture, whatever side the angle is touching is considered the adjacent. Whatever side the angle is not touching is considered the opposite. You can see how it's touching here and here. One of those is going to be the hypotenuse because it's the longest one. The other one that is touching is the adjacent. As for how the acronym works, just in case you aren't familiar, the first letter of the acronym on each of those stages refers to the circular function that's being used. So S for sine, C for cos, T for tan, and then the last two letters are the order in which you do your division. O over H, opposite over hypotenuse, so on and so forth. You can use that to do stuff like solving the trig ratios, right? So you have your triangles, you can just figure out one of the ratios. Sine theta, based on the information provided, we know sine is opposite over hypotenuse, angle is here, so that's the opposite, this is the longest length, so that's the hypotenuse. Sine theta is therefore the division of those two things. If one of your side lengths is unknown, it's only kind of not unknown, because you can still treat it as a variable which you can use, in the sense that what we can see is we have the hypotenuse, but we also have the adjacent. We don't know what the adjacent is, but we do know that it's x. So we consider that when choosing our circular function that we're going to use. We need to use the one that has adjacent and hypotenuse in the equation, for which cos is the only one that does that. Then all you got left with is the x that you're trying to solve for, so you just do your rearranging. That's just a matter of multiplying both sides by 4. Tech-free, that's how you leave it. That's the exact form. If for whatever reason you need it to be in terms of a decimal number, just make sure your CAD is in degree mode rather than radians, because in this case we were given it in terms of degrees. If this said pi over 4, for instance, you'd want to make sure it was in radians. So that's what this looks like. The thing at the top there for the TI, or the thing at the bottom down here for the Casio. You can manually touch those. You can click those and have them toggle. Already covered basic trig? Yeah, so we've covered it before, but in probably a different class. This being the Unit 1 and 2 one, people are getting into circular functions for the first time for Unit 1 and 2, so we're just getting some of the basics done before we get into the other stuff. Yeah, all good, all good. Okay, and then lastly, I guess for solving the unknown angles, so we don't know the angle, we do know the two lengths here. This is the opposite, this is the hypotenuse. And so, again, opposite hypotenuse means you use sine, because that's the one that has opposite hypotenuse in it. That gives you sine theta equals a half. And the way that you solve this, or write your answer, at least as of now, pre-learning some exact values on the unit circle, you write it as follows, where you do the sine inverse. So what you have is an equation that says sine theta equals a half. What you're doing by getting the theta on its own is actually something that's probably not really focused on too much as far as what math is actually happening here. It's got to do something with composite functions, oddly enough, actually. There's this property, which I'll pull up my notes up, the handwritten bit now, that we can start talking about. There's this property that works for all functions, which is if you have f of f inverse of x, what you get is x whenever the inverse function is in composition with its original, or vice versa, right? This one could have the inverse and this one could have nothing. Whenever that is the case, whatever's in the most inner brackets is what comes out. So when you have sine theta equals a half, what you're doing is you're applying the sine inverse to both sides as if it was any other operation like addition, multiplication, division, any of those that you do via your algebra. And so when all is said and done, when you're simplifying, you can now use this property where f and f inverse are applied to each other to just replace with whatever's on the inside. Whatever's on the inside, of course, being theta here. So those two cancel into each other, giving you theta equals sine inverse of a half. So that's like what's actually happening under the hood when you do that. That's just a nice little thing for when you do your composite functions and stuff like that. It shows you a little bit more about the applications of it. But okay, that's about it for some of the basics. Let's suss out the unit circle. So, unit circle in more detail. What we're doing, as I said before, is trying to find out, based on the angle that we're provided, what the coordinate would be, or the opposite. If we know the coordinate on the unit circle, what angle must therefore have given it? The way it basically works is the y coordinate is going to be given by sine of theta, the x coordinate is going to be given by cos of theta. The reason why is because of those trig ratios that we talked about, the opposite of a hypotenuse, the adjacent of a hypotenuse. The hypotenuse is that bit there. It's the bit that is from the origin to the outside of the circle. When it's a unit circle, that hypotenuse is 1. So, those fractions disappear, leaving you with just the opposite or the adjacent. And if you look at the triangle that we have, if theta's here, that one's the opposite, that one's the adjacent. And so, how far horizontal you go is purely dictated by cos, or in other words, your x coordinate is dictated by cos. How high you go is dictated by sine, so therefore the y coordinate is dictated by sine. This is what I think of when, well, at least initially, when I was trying to memorize, is cos or sine the x or y. You'll need to be able to be very, very confident with doing that, because the rest of this area of study relies on you to be able to pick out which one's which. Okay, next up, how do we now start using this? There will be a lookup table of exact unit circle values that you'll need to have memorized. This will not be on your formula sheet, unfortunately. It can be in your bound reference, perfectly fine, but you will need to have this memorized for the tech free, and they will pretty much always ask a circular function question in the tech free that relies on knowing some of these values. So definitely need to have this memorized as early as possible so it's not an issue in the real thing, or even the SAC for that matter. But okay, so first up we're going to look at the simpler ones, which are going to be the quadrant boundaries. So if you imagine the xy axis having the 4 quadrants, you can also imagine the unit circle having the 4 quadrants. And again, if 2 pi is a full revolution, then pi is a half revolution, pi over 2 is therefore a quarter revolution. So all of these values are separated by that quarter revolution, pi over 2. The numbers for this are quite simple. Those are just the x and y values of 0 and 1 and negative 1 respectively, based off of whether x would be positive or negative, and based off whether or not y would be positive or negative. For instance here, if this is the origin, then all the way right would be an x of 1, since it's on the right side of our axis, and it'd be a y value of 0, because it hasn't risen at all. In the other example, this has an x coordinate of 0 because it hasn't gone horizontal anywhere, but it's gone as vertical as is possible. Y coordinate 1. Same thing with the negatives over here. So, when it comes to your sine and cos values, since sine is your y and cos is your x, all of those sine and cos values that you see there for different values of pi, different angles, are going to be anywhere between -1 and +1. Tan, however, is a little bit different. Tan, by definition, is the division of sine and cos. It is sine divided by cos. So you have a couple of options how you want to handle this. You can memorize these as well, or because you have your sine and cos table, you can just do the sine value divided by the cos value. 0 divided by 1, 0. 1 divided by 0, undefined. So on and so forth. So you can either have those memorized, or you can calculate those as needed. That's entirely up to you. Ideally memorized, because you want to be able to spot a value or a number and know immediately what angles that could associate with, rather than having to calculate it every single time. Like for context, that was what I did. I tried to calculate it in the actual in the exam. I never memorized my tan stuff. Probably should have. It didn't bite me in that exam specifically, but it would have been better if I had memorized them. There's only a few more values. Next up are what I'm referring to as the interquadrant angles. So you've got the quadrants, boundaries, and you've got whatever's on the inside of that. Like these ones, for instance here. The pi on 6, the pi on 4, and the pi on 3. These are other ones you'll also have to have memorized. There's no real nice and easy way to have these memorized. Yes, there are things you can think of, like they are ascending, 1, 2, and 3, and you just do square roots of them, and they're all divided by 2. Yes, they have these similarities between them. But at the end of the day, it is pretty much just going to come down to memorizing it, however you want to memorize those values. At a bare minimum, you need to know the angles pi on 6, pi on 4, pi on 3, and the exact values half, root 2 on 2, and root 3 on 2. Everything else is just a slightly rearranged version of that, or a division of the values that you already know. What you'll typically see is those will be expressed on a unit circle. Now, for those who haven't done the unit circle before, or need to practice doing it again, this is where you unfortunately need to spend some time, 2 minutes or so every day, and I do mean every day, ideally even a couple times a day, just drawing this out. Yes, there's a lot on here, and we're going to show you how to better memorize what's going on, but at the end of the day, you do need to have this memorized one way or another. The way I would personally start memorizing things is to focus on just that first top quadrant there, because what you'll soon see is that the values in here are essentially just reflected across to any different quadrant. So if you know what's in the first quadrant, you can reflect those across to the other quadrants as well. So, how do we start putting things together? Well, the easy part is writing the angles in ascending order. Right? So you start with your angle of 0, the next smallest is pi over 6, the next smallest pi over 4, so on and so forth, until you get up to the quadrant boundary of pi over 2. That's the easy bit. And you can just keep counting around. Like for instance, pi over 3 just means you are splitting this top half into 3 sections. You've got the 0, the pi over 3, 2 pi over 3, 3 pi over 3. The pi over 4 is splitting it into 4 sections. That's why you'll see a pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Pi over 6, same story, 6 sections. So that's how you continue to count around the rest of the unit circle until you hit your 2 pi. From there, how do I arrange my values? The root 3 on 2, the root 2 on 2, and the half. Think about, at least in my opinion, it's best to think about this in terms of the position of the x and y coordinates. So like let's say for this pi over 6 value here, it is as far right as possible as far as the other ones are concerned. It's the rightmost one, which means that the x coordinate that you give should be the biggest of that list. Root 3 on 2, root 2 on 2 are half, root 3 on 2 is the biggest of that list, and you're going to assign that to the x because it's as far right as possible as compared to the others. Oppositely, as far as the y value is concerned, it is the shortest one. these other two angles have a bigger y value. They're taller up the y-axis. So the smallest of those exact values gets assigned there. Biggest x, smallest y. Then when you look at pi on 4, it's the middle of the pack in both ways. Right? It's middle of the pack for the x, middle of the pack for the y. So it's going to get the middle of the pack coordinates. Root 212, root 212. And then finally the pi on 3 is effectively just going to be the opposite of the pi over 6, because you're as far vertical but less far horizontal. It switches around. So you can see the x values in the anticlockwise direction are getting smaller over time, and the y values in the anticlockwise direction are getting bigger over time because you're getting further up. Any questions about that first quadrant? What you'll notice is that they're all positive. And the reason why they're all positive is because they are in that first quadrant. This is where positive x's go, this is where positive y's go. So when you're over here, you get both positive x and y. If we look over here, this is where we should expect negative x's and positive y's. And sure enough, if you compare any pair of these, they have the exact same coordinate set with the exception of negative being on the x. Even similar, this is normally where you have both negative positive and both negative x and negative y. Sure enough, if you again compare each of those pairs, they are the same numbers, but both are now negative as opposed to just the x. This works horizontally and vertically from any given pair. So should you, as long as you can understand this first quadrant, you'll be able to flip those values across to the other coordinates, the other quadrants rather. Any questions about that one? Okay. This I made myself, the tan unit circle, because you do need to know your tan values. You don't, again, you can just calculate your tan values no matter what, should you decide not to memorize them. But if you do want to decide to memorize them, here's probably the best way that I could think about. At least this is what I do now to memorize my tan values. First is the values themselves, you just need to know. But as far as where they go on the unit circle and where you're organizing them, because tan is sine divided by cos, and sine is y and cos is x, another way to think about tan is just y divided by x. And y divided by x is gradient, it's rise over run. So with that in mind, as long as I know my values, I'm going to look at the angle of those lines, and whichever one's the steepest is going to get the biggest gradient, whichever one's the shallowest is going to get the smallest gradient. So thinking about these values in terms of the gradient of the line itself. Like if you see this blue line here, this is visibly less steep than the black line here, which is also visibly less steep than this blue line, which is why these go in ascending order. Right, the gradient's getting steeper and steeper until it gets perfectly vertical, which we all are now familiar with, that perfectly vertical means undefined gradient. You have a run of 0, and anything divided by 0 gets you your undefined. That's why you also end up with positive, actually I'll take a step back. Now, as for why these are positive and these are negative, it's got to do with the slope of that line. If you think about this blue line here as a linear, that's got a positive gradient, which is why it's positive here and here. Those lines, if you keep track of them, have that positive gradient. Whereas these ones are descending from left to right, which is why they have negative gradients. So those are the main things to watch out for there. Any questions at all? And again, this is something you can either memorize or calculate. Up to you, though you'd be best served memorizing them, but I can sympathize with calculating because that's what I did. Okay, we've now got our unit circle. What the hell are we doing with it? we are using it to do a couple of things. One is what's referred to as evaluating the circular function. The other is referred to as solving the circular function. Those are two separate things. Evaluating is when you are given the angle. So if it says evaluate sine of 3 pi on 2, you'll see they're giving you the angle, but they want to know what the value is on the unit circle. Solving is the opposite. They give you the value, like root 3 on 2, and they say, figure out what angle gives you that. Today, we're just going to look at using our unit circle to evaluate the circular functions. So let's have a look. It's a two-step procedure. First, you just look at the angle that it says, whatever's in the brackets. This one says 3 pi on 2. So I pull up my unit circle, or my memory, and I locate where 3 pi on 2 is on the unit circle. And I have a look at the coordinates that are responsible for that. I've got 0, negative 1. Next, I'm looking at the circular function itself. If it's sine, I'll give the y. If it's cos, I'll give the x. This is of course sine, so I give the y coordinate, negative 1. If it was cos, I would give 0. Any questions about that so far? And if I go too fast, just let me know in the chat. Happy to go back on anything. Now, one of the complications here is that you might have an angle larger than 1 revolution. For example, 7 pi on 3 is bigger than 2 pi. You will not see 7 pi on 3 on this unit circle. These questions are quite simple. You're just looking where is it on the unit circle and then just writing out the x or the y value. These questions force you to work a little bit harder because it doesn't look like it appears on the unit circle. What do? Well, if it's a small enough angle, if it's not that much bigger than 2 pi, we can just keep counting around the unit circle. Like if you remember the whole idea of the pi over 3 splitting your semicircle into 3 individual coordinates, you can just keep counting. Pi on 3, 2 pi 3, 3, 4, 5, 6, and then 7. That's the one that we wanted. So the bit that we end up on is the coordinate that we're going to choose to use. So in the context of circular functions in the unit circle, 7 pi on 3 is functionally identical to pi over 3 as far as angles are concerned. So we go to the pi on 3 spot on the unit circle. We're just counting around. Then from there, the rest is the same. If it's cos, you give the x, which in this case it is cos, so we're going to give the coordinate of a half in that case. If it's too big to count, like no one wants to count 55, then here's what you can do instead. And this also works for smaller ones as well. It's the same idea. What we're effectively doing here is breaking down our improper fraction into a mixed fraction. So 55 pi on 6, we want to figure out how many times does 6 fit into 55 with what remainder. In this case it is 9 times with 1 remainder. Now because we got pi in that coefficient, in that top bit, we're going to have pi in both our quotient and remainder here. So 9 pi times plus an additional pi over 6. That's great and all, but what do we do with that? Whatever the whole number, the integer value of pi is going to tell you where to start on the unit circle. Because if you think about, again, how we're counting around the unit circle, if you count in terms of pi, starting at 0, you go to pi over here, 2 pi is over here, 3 pi is over here, 4, 5, 6, 7. All of the odds are on the left-hand side. All the evens are on the right-hand side. So when you have 9 pi, it being an odd number, that tells you you should start here. So this could be as huge of a number as you could imagine. So long as you can tell whether it's odd or even, that'll tell you where to start counting from, rather than here by default. Then, whatever's left over, you just count whatever's left over. So you're always going to start either the left or the right hand side of the unit circle, and then whatever's left over is going to be sharing a denominator with one of these values, and so you just go to the one that makes sense. So if it's plus pi on 6, you want to go to the next pi over 6 value. If it's plus 2 pi on 6, which would just be pi over 3, you go to the next pi over 3 value. So on and so forth. Any questions there? You'll be using this one more so than the other thing, because usually if they're going to do this, they're going to give you a big angle to work with. Alrighty. Oh yeah, and then for the evaluating, again, just wherever you left off with, that is the spot, and so you give either the x or the y, which in this case being cos, you give the x. So final answer, negative root 3 on 2. The last is the negative angles here. So the way I would think about this, yeah, let's take a step back. So what does a negative angle mean? You'll notice that when I was counting out the angles in positive world, I was doing it in an anti-clockwise direction, going in this direction. When the angle is negative, what you're doing is you're starting at 0, but then counting in the clockwise direction instead. So what that might look like would be this, where you now start at pi over 6 down here, rather than here, and then so on and so forth, all in the negatives. That's fine. You can think of it as that, which it is. That's what it actually is. But I think there's a little bit of an easier way to actually do this, because for whatever reason, getting your head around negatives is usually harder than getting your head around positives. By following this procedure, you pretty much just don't care that's a negative at all. So the first thing that we're going to do is look at the angle that we have and pretend that it's not negative, and just locate the positive version of it instead. So that's going to be there, 7 pi on 6. Next, to handle the negative, all we do is flip upwards. So whatever is directly vertically above or below the value that you found, depending on where you started, is the negative version of the angle you're trying to find. So that gets you to 5 pi on 6, which of course now means you're picking either the negative root 3 on 2 or the half. This is sine, so you're picking a half. Another way to think about this could be the same way you think of reflections in other functions. When you have f of negative x, well, more so it's when you have negative f of x, where you flip vertically. It's the same sort of idea. It's just expressed a little bit differently, because what negative and positive means in terms of angles is a little bit different too in terms of the variables. So it's a little bit different, but you can treat it effectively as a flip vertical, as a reflection. Okay, that's where the lecture portion on this one ends. Are there any questions about any of that so far? In the meantime, I'll get some of these photos going so we can use the unit circle together to practice. Okay, that's the unit circles all sorted. Next up, we're going to do a bit of practicing on the evaluations. Okay, let's start with perhaps a relatively basic one. So we've got the angle of 3 pi on 2, and we want to figure out what sine and cos are of 3 pi on 2. Let's just start with sine. So we want to figure out what is sine of 3 pi on 2. How do we do that? I'll also get a screen grab of the summary so you can see the steps. It's a two-step procedure. Step 1 is just locating the angle that we want on the unit circle. this angle is 3 pi on 2. So we look at our unit circle. There it is, 3 pi on 2. Next, based on the coordinates that are provided to us, we're going to give either the x or the y. Sine is the y, cos is the x. So, if sine is the y, that means we're going to report -1 as our value here. And that's it. Two-step procedure. Those are the basic ones there. If you can spot your angle directly on the unit circle, do that. Give the x or the y, depending on if it's sine or cos. So if it was cos 3 pi on 2, that would have been 0. Because again, if we look back at the 3 pi on 2 spot, the x coordinate was 0 there. Tan of 3 pi over 2 doesn't appear on the unit circle. The 3 pi on 2 bit does, but we don't have tan values on this. We have x and y. You have two options here. You either calculate it by doing the y divided by the x, so -1 divided by 0, which would give you undefined, or you have your tan unit circle, which also has undefined written there as well. Those are your options. Next up, let's practice one of the negative angles instead. So I'm going to make one up. I'm going to do cos -3 pi on 4. I'll pull up the procedure for that. Let's see if we can figure it out. Yeah, all good. Happy for you to leave. No worries. I'll leave you to it. Thanks for coming. Okay, so first up, the procedure says that we should be locating our angle on the unit circle, ignoring the negative portion, so just finding the positive version of it. So if we have, hang on, is it the 5 pi on 4 spot? Let's have a look. So 5 pi on 4 is there. Yes, it is going to end up being that spot. Absolutely. Yeah, you got it right. So how you got there was one of two methods probably. You either just counted backwards the -3 pi on 4, so that would be -pi on 4, -2 pi on 4, -3 pi on 4, and that gets you there. Alternatively, you could have then said, okay, well I'm going to strip the negative off and look at the positive version, which is here, 3 pi on 4, and then because it was actually negative, I flipped downwards, and that would also get you there. Which way did you go? Did you do this method or did you count around? Yeah, okay, that's fair. And I like it too, because it helps with the more challenging ones. But cool, yeah, that's it. So that gets us to that spot, but that isn't the final answer. That just gets you to the angle. So we get the coordinate now, which is -√2 on 2, comma, -√2 on 2, which is, well, you don't really have a choice here, but let's make it a bit more obvious than just that. Do we give the x coordinate or the y coordinate, given that we have cos here? I know they're both the same, but x or y matters for cos. Got a 50-50 shot. I'll pull up, yeah, this. That'll help maybe. So coordinates are always written in terms of cos theta, comma, sine theta. So looking at that notation there, given that we have cos, is cos in the x spot or the y spot for that coordinate? Yes, x spot, correct. So whenever you have cos, you give the x coordinate. So again, if we look back at what we had, negative root 212. Now again, they're both the same thing. It didn't matter here. But if it was literally anywhere else, any other one that wasn't a match, then it wouldn't matter for you to say the right one. Negative root 212. Okay. Last up, we'll do a bit of practice on the big nasty angles where they're massive. Just see if we can simplify those down. Let's start with what looks like the toughest one. 211 pi. We've got to figure out sine and cos of that. It's fine if we just get to the right spot on the unit circle. So theta 211 pi on my unit circle. Where is that going to be? I'll pull up the... yeah, I'll pull up this one so you can use that as a reference. So just trying to think, where would 211 pi be? Like, what spot is it taking on the unit circle? The way to do it's in two steps. First, if you have a improper fraction, you want to convert it into a whole number and a fractional value, so the quotient and the remainder. This one is a whole number, so you've already kind of done that. Next, we're looking at that whole number, and then based on whether it's odd or even, will tell us where we start. 211 is odd. That means what? It tells us something. We're on the left side, exactly. If you have an odd multiple of pi, you start on the left. Because again, if you remember how we count, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, all the odds are over here. So we start there. And we're going to finish there actually, because that's all there was. So, whatever's at that coordinate, whether we're doing sine or cos, will depend on whether we do x or y. If I then had plus pi on 4, I'm just going to go forward another pi on 4. So if we look at the unit circle that we have on the screen share, again we're starting here, but because we're adding pi on 4, we're going to get back to the spot that we had before actually, the negative root 2 comma negative root 212 spot. The same one there. So all that to say, because this is repetitive in nature, it circles around, there are a lot of ways of expressing the exact same spot on the unit circle. Now, if you have both a nasty big number and a negative, you're essentially combining the two methodologies together. Now, for the whole numbers, it's less tough because you just kind of flip again, right? So 53 would be odd, but because it's negative, actually no, that's not how that will work, because for the whole numbers, the flip is vertical, not horizontal. So whether it's negative or not, you kind of just leave it there. But for the fractions, it matters a bit more. So let's say we're doing our negative 9 pi on 2 here. Negative 9 pi on 2. First, we're going to try and convert that to a mixed fraction. We want our whole number, we want our remainder. What's that going to look like? I'll pull up the example again. pi plus half pi. Yeah, that'll be it. Alright, wait, hang on. So that's going to be, hang on, did I misread that? Let me have a look. Oh, right, because you got our, yeah, no, I gotcha. I saw the 45 there, must be a typo. Yeah, so 2 fits into 9 4 times with 1 remainder. So you're going to have your 4 pi and then a remainder of pi over 2 there, or half pi. Now, these are considered negative, but once we've flipped this up, all we're going to do is fix that up. Oh, you saw 91. Oh, okay. Yes, that's that is my fault. Yeah, pi over there. But all good. Happy accident. Yeah, and then so from here, because it's a negative number, we start by just ignoring the fact that it's negative and going and doing exactly what we've done before. So because we have 4 pi, that being an even one, means we now start here, plus pi on 2, well, the only other pi on 2 spot is directly vertical. And then finally, because it's negative, instead of being up here, we flip it vertically down to here, which is going to get us to the 0, -1 spot. Which one do we even have? Oh, it was both. So what's sine and what's cos there? So sine would be the y, -1, cos would be the x, 0. So when you have your final answers, sine -9 pi on 2 would be -1, since the y value is as low as it can be. Cos -9 pi on 2 is going to be 0, since the x is perfectly vertical with the origin. It doesn't go horizontal at all. That's pretty much it. Those are the most challenging ones there, where you have both a big, or, well, maybe not too big, but nasty-ish angle that is also negative. You just do it in 2 stages. Most important stage is going to be breaking that down into simpler numbers to use, the odds and evens approach, and then finding where your spot is on the unit circle, and only then do you consider the negative at all. Alternatively, you could again just count around the unit circle, but the negative version of it instead, and do it that way, but this is probably just a bit nicer, because you only need to have 1 circle memorized, and then the rest of it is just doing a bit of what's effectively fraction math. Like this is your year 6 stuff, so that should make life a lot easier. That pretty much covers everything for the lecture portion on this. If anyone had anything specific they wanted to have a look at, let me know. Otherwise I could just introduce the next couple of topics for circular functions. So I'll start pulling that up now, but feel free to hijack that and ask any burning questions, because we're essentially done with the plan for this one. And if I start talking while you're still writing one, just continue writing it. I'll go back to it. But in the meantime, the next portion of what this will lead into is the solving of circular functions. Now, I said in the beginning there's 2 kinds of questions. One of them, like we've just been doing, is when you have the angle and you want to find where it is on the unit circle. The other is this kind of thing. You'll see the spot with the angle in it is x. There's nothing there. But it's actually the equation this time now. It equals something. Cos x is equal to √2 on 2. Not only that, but you even got a domain with it as well. So there's a few little things you can be able to spot immediately to know when I'm doing this procedure versus another procedure. There's a domain involved, there's an equation involved. What do we do here? Well, our goal ultimately is to figure out what x is. But because x is in the angle spot, we've got to handle things essentially backwards to what we just did before. I've got a full procedure written out here, but that's a lot of blue text. So let's just see how to do it instead. The first thing I want to do in all these questions is make sure I have what I'm referring to as an exact value expression, which means I want to have my circular function on one side of the equation and one of the unit circle exact values on the other. I always want that no matter what when it comes to solving equations that have circular functions in them. In this case I do. I've got cos on the left and I've got root 2 on 2 on the right. Root 2 on 2 is one of those values. It's this one. It's one of those values on the unit circle. So we're happy. Step 1 has been achieved. Step 2 is for more complicated stuff. We may or may not look at that today. Step 3. I want to look on my unit circle and find every spot where cos is root 2 on 2. Or in other words, where the x-coordinate is root 2 on 2, since it's cos. Now one of the things you'll need to get your head around, just because this says x does not mean you're always looking for an x-coordinate. Little x is the variable you're trying to solve for. The coordinate that you use is dictated by sine or cos, whatever the circular function is. Tan as well, but usually it's going to be pretty much always a sine or cos thing. So because it's cos, we're looking for which x-coordinates are root 2 on 2. Well, there. That's an x for root 2 on 2, and that's a root 2 on 2. That's also in the x spot. What angles give that? Well, that one and that one. That's our answer. That's all there really is to this, at least in the most basic version of this kind of question. There was a domain associated with it, 0 to 2 pi. And because that's little x, we're saying that our angle is limited to be between 0 and 2 pi. Now what that means is 0 and 2 pi. One full revolution of the unit circle, which is why we were able to hit both those spots together. If the domain was 0 to pi, for instance, we couldn't go past this, so we only get this one. Alright so far? Any questions about this or otherwise? This is an example where some rearranging might be required, so step 1 needs to be done. We do not have a circular function on its own, and we technically have an exact value on the unit circle. 0 does count as one of them, but the first criteria isn't met there. We haven't got the circular function on its own. So let's do that. Add root 3, divide by 2. Now we can solve it. Exact same thing. So it's sine equals root 3 on 2, so we look for where the y values are root 3 on 2, and then give the angles associated with that. Here's that bit on the domains. So instead of being from 0 to 2 pi, we now have negative pi to pi. The way you work with these is to split them up into positive and negative sections. So for instance, negative pi to pi can be split into 0 to pi, which is just from that top semicircle, starting at 0 and ending at pi. And the other half of that is from 0 to negative pi, which is going to be this bottom part of the semicircle. What you're going to essentially do is evaluate those individually. So sine x equals 0. First I want to look at my positive half of that domain and look at all the spots where the y values, sine, is equal to 0. Well, y value of 0 here, y value of 0 here. That means the angle of 0 and pi are both valid for this. Next, I'm going to handle my negative section, which is now from 0 to negative pi. That's going in this direction. So, what do we get from there? Well, we hit 0 again, and we hit the pi, we hit negative pi, right? Because we've hit this spot, yes, but because we're going backwards, every value that we hit is now a negative value. And so we've hit this spot once, and kind of like this spot twice. Once as a positive direction, once as a negative direction. So we just write them all down. Here's that 0 and pi that we started with, and we don't duplicate angles, so we don't say x equals 0 twice. We just, the only way you can duplicate angles is by saying the other version of that angle. So for instance, because we hit pi and negative pi, we're able to say both of those because those are considered different because they have been arrived at in a positive versus negative direction. Just anything that fits in here. Like you wouldn't be able to say 2 pi anymore because although 2 pi is functionally the same as 0 for the angle, it is outside the scope of this domain. So we can't use it. That's it. You just give that as a final set of values. I've done it as separated by a bunch of x equals signs with commas. You could also use something like, if you want to be fancy with it, you could say x is an element of, and then use your curly braces to denote individual values. Negative pi, comma, 0, comma, pi. And that's your fancy way of writing those solutions without doing a bunch of x equals stuff. Both of those perfectly valid. Just use whatever's simplest. Okay. I think we'll probably save the composite function bit for later. It's fairly involved, and we've only got a few minutes left. So we'll do that the next go around when we have a full dedicated lesson for this portion bit. But what I can show you is other little funky things to at least think about. We're not going to have time to practice any of it, but just stuff so you can have seen it before we then go into detail and do it later. Something like this, right? Trying to get your exact value expression, you start looking at this like, well, what am I supposed to do here? I've got to get the circular function on one side, but there's 2 of them. How does that work? You kind of can, at least in this case, by identifying that there's a common factor of cos here. You've got cos squared and you've got regular cos. So you can take a common factor of cos out. Now why does that matter? We still got a bunch of crap on this side and then equals 0 on the other. Well, this is now null factor law, right? You got 2 sets of brackets equaling 0. So that allows us to create 2 separate equations. One where cos is equal to 0 and one where cos plus 1 is equal to 0. That's these 2 things. Now we've got it to a stage where cos is on its own and the exact value is on the other side. This one needs a little bit more rearranging. You just subtract 1 from both sides. Getting there. So you're able to take what is otherwise challenging and split it into 2 separate equations that you solve individually. The other thing that comes across is when you have 2 different circular functions and you're thinking, well, okay, what am I going to do here? Right, I can't really get one on the other. Is there like a... sometimes you can do like a sine squared plus cos squared equals 1 sort of thing, for those who remember that trig identity. But these aren't squared, these are cos 2x, these are sine 2x. Bit different. Whenever you have both sine and cos in an equation, it's a good idea to start looking to see if you can convert them to tan. What that means is, because tan is sine divided by cos, if I ever get to a stage where I can divide both sides of my equation by cos, which I do here, right? I subtract cos 2x to the other side and then divide both sides by cos 2x. Cos divided by cos is just 1, negative 1 because it was negative at the front, but sine divided by cos is tan. Sort of effectively done here is convert 2 circular functions down into 1. Now that it's 1, I can get that thing on its own and solve it the same way I solve other circular functions. So these are the kinds of things that show up quite a bit in the SACs and the exams, where they get you to do a conversion to tan or a null factor law thing. Anything previous to this, so like composite function and all this stuff, those are considered the basics. Like those are the bare bones, knowing how to do it. These last couple of examples are usually what the exam might be asking you to do, if it's specifically a solve question and not just a step in a multi-part process. Yeah, that's a little sneak peek for next week on this one. That's about it for time as well. I have talked a lot. Any further questions? Otherwise, I'll let you guys enjoy the rest of your day.
Thanks, Chris.
No worries. No worries. Have a good day.